Welcome to Chapter 3 of Physics Without Calculus for Aquinas University. Today we'll be going over two-dimensional kinematics from the College Physics 2 second edition textbook on open stacks. Two-dimensional kinematics is exactly what it sounds like. It is the motion of things when you have more than one dimension that you care about. One-dimensional kinematics is kind of moving on a map, right? Going northeast, south, or west. Two-dimensional kinematics involves flying through the air, usually. The next step, of course, will be three-dimensional kinematics, which is more complicated version of this exact same process. We talk about that in the calculus-based version of this sooner. I think we get to it in the physics base, but when we get to it, we get to it. So what does two-dimensional kinematics look like? Well, the classic is a ball, right? A tennis ball, for example. If you hit a tennis ball, if you ever play tennis, you are aware that you need to worry not only about the direction the ball is flying, but that it lands after the net, but before the end of the tennis court. Otherwise, it's a foul ball, doesn't count, right? So that calculation you do as a player in real time. If the ball's coming at you super fast, you don't necessarily want to hit it super hard in return because you might go out of bounds. This is what's done by the player in the activity, can also be done in math, and that whole process is what we'll be talking about here. So that's the classic, of course, is the ball, the object in motion. You can do a 2D kinematics conversation with the map as shown here. And this is basically the real world analogy to the trigonometry that goes on in this conversation. Because, well, if you are walking through a city, you walk down one street, take a left, walk up another street, you are however many blocks from where you started, right? In this case, 9 plus 5, you're 14 blocks from where you started. But your actual distance you covered is the hypotenuse between them, right? The C in this conversation. This stuff should bring you back to high school math when you covered trigonometry. And the equations involving triangles. The classic, of course, being Pythagorean theorem, a squared plus b squared equals c squared, where c is the long part of the triangle. Solving for a squared plus b squared equals c squared is taking the square root of the squares. This stuff hopefully sounds familiar to you. If not, please let me know. Work out with your classmates. Do some extra work to catch yourself up to this point. Of course, SOHCAHTOA, sine, cosine, tangent, all those are also part of this exact conversation. And again, using that trigonometry allows us to realize that traveling 14 blocks by road lands you at the same point as, say, a helicopter traveling in a straight line from starting point to destination. 10.3 blocks for the helicopter is 14 blocks for the car traveling on the street. And that's the exact math we're going to use. We're just going to give you more complicated questions revolving around this basic idea of using a triangle a bunch. How this game is played in regards to physics and kinematics, as I said at the very start, revolves mostly around objects in motion. You tend to just consider them all balls for sake of conversation, right? Pretty easy to draw a little circle on your paper. When you end up throwing a ball, or if you just drop a ball, the downward force, gravity, is applied equally to both. That's what this diagram is showing here. The red ball is just dropped, the blue ball is thrown, but gravity is pulling down on them in equal measure throughout. They're going to hit the ground simultaneously, essentially. The classic example, of course, of this is like rolling a ball off a table, and then as soon as the ball leaves the table, drop the ball, and you notice that both hit the ground at the same time, even though one has a horizontal motion. Again, more displacement graphs. I imagine you're getting this conversation, right? You can travel a varying distance to reach your destination, or you can fly straight to it. You're still in the same destination point, but flying straight is faster. Cool. As said in the previous chapter, I am going over selected questions. So some of these have questions in the textbook. I'm not covering them because a rehashing of basic trigonometry is something I am assuming you have at least some grasp of. You know how to use the sine, cosine, tangent functions on your calculator by this point. I'm making that assumption. If not, let me know. I can work on that with you. But how they got that theta equals 29.1 degrees, you should be able to look at this and realize how they got that as an answer for the direction of the helicopter flight. So this again is a question of the text I'm skipping for brevity's sake. Brevity's sake, there we go. But yeah, classic tip to tail method. There are questions here that go over the graphical determining 2D kinematics via graphical methods, like actually using a ruler and using a protractor. I'm not going to be having you do that stuff. I didn't put questions relating to actually drawing things out and measuring them with your eyes in the homework, because the application of a lot of these processes for Aquinas students, which is what this lecture is aimed for, are probably not going to be drawing stuff out, right? If you're a mechanical engineer, that may be one thing, but from talking with the other professors, most of you probably aren't going into a field where you're going to be hand drawing this stuff. And we have computers nowadays. We don't hand draw this stuff as much anymore. You did this in middle school and high school. You probably remember how to use a protractor. So how do you determine the total distance from a graph like this? Well, you can measure it all out, right? You can draw this on graphing paper, pull out your ruler and your protractor and get to work. That gives you an answer. But I'm more interested in, of course, anti-parallel, right? Negative signs, negative means opposite direction. We discussed this stuff last chapter. I'm more interested in the math side of this whole calculation. So that's why I'm kind of jumping the gun a bit too. If you're looking at these equations, you're like, I don't get it, right? Go to the textbook. I'm going to start in chapter 3, but chapters 1 and 2 over here on the left provide a bit more in-depth understanding if you need it. So there we go. Let's get to this side here. What we're looking at here is a breakdown mathematically, computationally, of that set of the triangle we've been talking about. Namely, we are putting things what's known as X and Y components. Okay. So the graph we're looking at here, compare that to 25, compare that to our street graph at the very beginning. Okay. We notice we start here at 0 and we move east, due east, right? Straight east for 9 blocks. And then we move due north for 9 blocks. That's how you describe this motion in like the real world, right? You walk east for 9 blocks, turn, walk north for 9 blocks. But the north, south, east, west cardinal directions also form the basis of the Cartesian coordinate system, that classic coordinate system that we all have been dealing with in math for quite a while. So if you describe motion on that classic coordinate system, you can describe things in purely X's and purely Y's. So the AX is all motion exactly and only exclusively in the X direction. And AY is all movement exactly and exclusively in the Y direction. And notice if you go in the X and go in the Y, your end point is the same as the hypotenuse, the boarded A going along the top. Meaning the A vector was what we'd call that. The bolded A can be described by the motion in the AX and the motion in the AY. These ideas are connected. And once you realize that these ideas are connected and that any direction, any vector, any motion in a 2D plane can be broken down into its purely X and purely Y components, that allows you to do kind of rather simple math to answer very confusing, complicated questions. We looked at earlier, I didn't go into it on purpose, but this guy right here, right? there's a lot of motion going around. Drawing all that on graphing paper, making sure it's 100% accurate to get your final measurements can be kind of a pain. But we can take these things, break them down into X and Y components, and then simply add up how many X's and add up how many Y's to end up the same net result. I'll go over some examples, as I said earlier, to expand on this idea here. The other cool part about this is, again, if you remember your trigonometry, how sine, cosine, tangent relate to triangles. The AX component can be derived purely from the A and the angle the A makes with the X plane, the horizontal plane. If you know A and you know theta, you can get your X and Y components using the equations shown here. A cosine theta and A sine theta. AX is A cosine theta, AY is A sine theta. Again, if you learn the acronym SOHCAHTOA, not acronym, you learn the phrase SOHCAHTOA in high school math, right? So opposite over hypotenuse, ka adjacent over hypotenuse, toa opposite over adjacent, right? That's all we're doing here. That's all this chapter is. So you can apply this again to the conversation we were talking before. Notice here, the fun part, we move the Y side of it from the right side of the C block over to the left. We turned this initial graph here, which was how you would walk. Where was it at? Here we go. We turned this how you would walk graph, and we instead made it look exactly like a Cartesian coordinate system. But you still get the same end result, because now you don't need to follow tip to tail like you're physically walking on the map, the graphical process. You can instead do the trigonometry of it and achieve the same end result. This image here is a explanation of all these concepts. In this case here, we're dealing with tangent, but it's all the same stuff. So let's look at an example, look at the math, see how all this plays out. Again, I'm going to the textbook here. You have access to the same textbook. You can see I'm passing a bunch of stuff of everything we talked about before to get to the particular question I want to get to. Feel free to pause the video, go to your textbook, read more in depth if you need that. Please do. I post the homeworks with plenty of time so you can go through this at your own pace. All right. Example 3.3. That's what we're talking? Yes. Same graph. Sweet. Add the vector A to the vector B. Again, a vector is a line, essentially, a scalar plus a direction. A is red, B is blue. Add vectors A and B using perpendicular components along the X and Y axes. That's the AX and the AY we were talking about earlier, perpendicular components. The X and Y axes along the east, west, and north, south directions, respectively. That's kind of convention. X is always east, west. Y is always north, south. If you want to know something different, you'll be told that it's different. Vector A represents the first leg of a walk in which a person walks 53 meters, 20 degrees north of east. And vector B is 34 meters, 63 degrees north of east. Probably the second leg of the walk. So you walk A, then you walk B. How far are you from where you started? And there's a lot going on there, but I said this a lot in chapter 2. I'm going to repeat myself here. The more you write down, the better you're going to do at this stuff. If you're given this question here, just that initial question, add vector A and vector B together, and you're like, I don't get it, try to draw it out. Draw it out in very simple terms like this. And if you want, do I have it with it? There we go. Draw it in very simple terms, and then if you have a protractor and a ruler, you can draw it in very exact terms and graphing paper, whatever works best for you. But you need to start by putting pencil to paper to figure out the answers to these questions. Okay, so we know some various things. We know A, for example, starts out at 0, 0. All right, A starts at 0, 0, and then A travels 53 meters. So our scalar product, the length of A is 53, and 20 degrees north of east. So this angle between the x-axis and A is 20 degrees. So go back to our math here. We know that A, bolded A, and we know theta. Cool. So we can look at our equations. Again, the equations are listed on this page. Scroll, find them, right? We can go on to our equations. We can figure out the x and y components of vector A. We know that the x component of vector A is equal to A times the cosine of the theta. So plug that math in, you get the vector component for A being 49.8 meters. So along the x-axis, it's 49.8 meters based off of the equation for the x-axis of A. Do that same play for B, right? Bx is equal to B cosine theta of B. And we know B is 34 meters long, so this blue line is 34 meters long, and 63 degrees north of east. Same direction, right? This angle that B makes is 63 degrees off of the flat axis. This graph, I think, does a better example of that. Notice the dotted line running where B starts. That's where we're drawing the 63 from. And of course, you do your math, 15.4 meters. So you can determine AX and BX from that equation. Once you know AX and BX, you know the entire length along the x-axis that AX and BX travel, which is the bottom part of that graph we're looking at. And you can do the same thing for the y components by using A sine theta and B sine theta for A and B respectively to get your 18 and your 30, 18.1 and 30.3 meters. So that is how tall A and how tall B are going up the y-axis. So once you know those, you can add them together to get how long along the x-axis you traveled and how long along the y-axis you traveled. Just add them together, right? The total trip of the entire guy here along the x-axis is 65.2 meters. Along the y-axis, 48.4 meters. So now essentially I can make a triangle along the x and the y-axis. So I know the, let me go back here. I know AX and I know AY. Therefore, I can find A and theta. I can find my new A and my new theta, which is done with Pythagorean's theorem and tangent inverse. All I'm doing is trigonometry. All I'm doing to find my answer. And then here we have a super messy looking version of what we just talked about that goes through and breaks down every single component. Again, I'm going to repeat myself here. If you are struggling with using the equations involving sine, cosine, and tangent, you need to let me know. You need to let your friends in class know. You need to let the physics tutor know, someone to catch you back up to that level. Because if sine, cosine, and tangent are posing issues for you, it's only going to get more hard from here. Cool. So what about negatives? Well, as we discussed in chapter 2, a negative is merely a direction. So a negative component would be a component in the opposite direction. If you're moving like south, you're moving the opposite of north, right? So here we have someone that moved some direction and magnitude A, but then B is the opposite direction and a lot of magnitude. So, well, but you can still derive your X and Y coordinates the exact same because B makes a triangle. B has a scalar. B gives you a angle that you can determine, and then you can still draw out exactly what's going on. I guess in this case, the Y and X components of B are negative, so they would subtract from A, and your resultant R at the end here, still calculating the same way you calculated this. Exact same stuff. Just when you're doing this math, make sure that your parentheses on the correct location and not screw up your calculator, right? And again, when you're doing this, again, feel free. If you're like, I don't get how that works, go to the book. I provided lots of examples on how to do this stuff. So that is pure triangles, right? That's not living in the real world. When we enter the real world, we have to deal with a couple other components, namely arc motion and gravity. The math is along the same lines, lots of SOHCAHTOA, addition, subtraction, but the equations get a little bit harder. They get a little bit harder because you have to deal with changes in the way things behave. This graph here does actually a pretty decent job of explaining what happens when you throw something up in the air, right? Take a baseball, you throw it, you hit a tennis ball, something like that. You're applying a motion that appears to be an arcing motion, right? Imagine hitting a baseball, right? Flies way up in the air, that comes back down. But that motion, even though it's looking like a smooth arc, is actually a bunch of X and Y forces being applied to the thing that's in motion. At every single snapshot of the balls of a projectile's flight over an arc, you are doing nothing more than this. You have some X component and some Y component affecting to create your total direction. And that's what these little snapshots mean, right? When you initially hit the ball, or initially throw the projectile, you have some X direction, which is at this level, we consider basically unchanged. You're moving forward. And then the Y component is the force you put in to throw it up, fighting against the force of gravity pushing down. And when we get more in depth into gravity, I'll explain how that all works. It's fun stuff. But every single one of these snapshots, just the angle and the scalar or the magnitude of the purple V vector there is calculated purely by the X motion, which in this case is unchanged. As you can see, the blue arrows are basically the same, and the Y motion, which is decreasing and increasing as it travels. Let's do some math about this. Let's go to example 3.4. This page has all of your equations you need in a nice section here. You scroll back to this section if you need to go over the equations. I will point out real quick, hopefully you know how these variables work, but just as a reminder, X is position, right? X along the X-axis. If you see any Y's, that's position along the Y-axis, and X and Y can be interchanged depending on what you're asking. V stands for velocity. The little subscript 0, sometimes we just call it V naught, for example, is your initial velocity, and V without any subscripts tends to be your final velocity or your velocity at that moment. T is time, and A is acceleration. If we're dealing with gravity, A equals gravity. So sometimes these equations will be replaced with a G, and gravity will be whatever you're talking about, usually 9.81 meters per second squared. That'll be understood better when you do the math. Actually, yeah, negative 9.81 is technically what you'd want to use, because gravity always goes down, and convention states that Y is up positive and down negative. All right, so let's do example 3.4 together. A fireworks projectile explodes high and away. During a fireworks display, a shell is shot into the air with an initial speed of 70 meters per second, at an angle of 75 degrees above the horizontal, as illustrated here. Cool. Again, I'm going to stress this. Write things down as you're trying to solve them. If you're not writing stuff down, you get lost. You probably should have written stuff down. The fuse is timed to ignite the shell just as it reaches the highest point above the ground. So, given that information, calculate the height at which the shell explodes, how much time passes between the launch of the shell and the explosion, and what is the horizontal displacement, how far away from where you shot it will it explode. Cool. So I'm asking 3 different things here. I'm asking for a height, a time, and a horizontal distance. Cool. So what do we need? Well, we go back to our equations. We write down our knowns, and we find equations that help us solve our unknowns, right? Again, these are the equations. And these are those exact equations, but we're going to swap X's and Y's as we move forward. So, by height, we mean the altitude or vertical position of Y from the starting point. Y is height by convention. So we treat all the y's in the equations as referencing height. The highest point in any trajectory, called the apex, is when the velocity at y equals 0. What does that mean? Well, it goes back to this equation here. Notice the highest point here, there's no orange component. That's because you've hit the point to where your horizontal acceleration has been completely canceled out by gravity, but gravity has not started exerting motion down yet. The forces have ran into each other and they are a dead stop. That is the point to where you are no longer going up, but you have yet to start going down. And that's the apex. So, since we know the initial and final velocities, as well as the initial position, we can use the equation shown here to figure out that answer, right? We know V naught, y, because that's something we can calculate based on the initial speed, 70 meters per second, and the initial angle. Again, remember, any directional component, any direction involving here is not simply the direction that it is, but it is the direction given by x and y components. If I shoot something off at an angle, there is some horizontal motion and some vertical motion. So I'm not shooting the firework off at 70 meters per second in the y direction. I'm shooting off at 70 meters per second, 75 degrees above the horizon. So some of that 70 is in the x direction, some of that 70 is in the y direction. And this graph here illustrates some of the stuff I'm talking about. Actually, kind of gives away the answers. Because your location in the y and your velocity in the y are both 0, you can take this equation that we talked about before and simplify it down. Your ending y velocity, so Vy over here squared, is 0, because, again, we're defining the apex as where you're not having any velocity in the y direction. You've stopped ascending, and you have yet to start descending along the apex. And, again, our y naught is 0 because you're starting on the ground. So this equation, if you cancel out Vy and cancel out y naught, you end with 0 equals V naught squared in the y direction minus 2gy. And then in this case, y would be your height that you're trying to solve for. Rearrange for y, plug and chug, give yourself some answers. But wait a minute, that's velocity, initial velocity in the y direction. So we don't use 70 here. We take the a equals ay sine theta, and we use that to figure out what the y component of our initial velocity is. In this case, plugs the numbers in, you get 67.6 meters per second. The y component of that firework is 67.6 meters per second. Now we have an initial velocity that we can square for our numerator. We can solve our denominator at the bottom and find out that the firework travels 233 meters up before it explodes. The explosion up here, 233 meters. Again, kind of gave away the answer with the question. That's not the point. Cool. Let's solve for B. B is time, I want to say, right? Yeah, how much time is between those two. So we know how high it goes from solving A. So let's use that and find an equation that has a t in it for time that has all of our nodes. And again, I'm going to keep stressing this throughout the class. Everything should be written down. You should have your knowns in a little table as you're doing these problems, and you filling it in as you're solving. If you're trying to just do this stuff in your head and you get lost and you can't figure out what happened, maybe you shouldn't be trying to do this stuff in your head. Proper note taking is key, especially when we get to more difficult classes. So we find an equation that has a y naught, a v naught in the y direction, a v in the y direction, things we all know, and a t. Rearrange to solve for t, and we get 6.9 seconds. Excellent. Okay. C was how far away in the x direction is the thing traveling. Well, if we go back to our example shown here, x direction is unaffected by y direction. We'll imagine like no air resistance for these questions because that's just needless extra math. It doesn't go to the point what we're talking about. But going up and down and gravity and all that in the pure y direction doesn't play effect in the pure x direction. So if we can figure out our initial velocity in the x direction, and we know how long it takes to explode, we then can use that math and do a simple distance equals velocity times time equation. But we need to figure out velocity in the x direction, in this case, 18.1, because a equals ax times cosine theta, and we know a, and we know cosine theta. Sorry, ax equals a times cosine theta. I apologize. Solve it out, 125 meters. Bam. Excellent. These equations are using the same couple, these questions are using the same couple of equations, the same trigonometry ideas over and over again, but layering them in a way that they all connect with each other. That's the important part. You need to realize this question was good and that it had you do A, solve for your initial height before it asked you to solve for time, before it asked you to solve for distance, because you needed to know how high it went up before you knew how long it took to get there. The questions aren't always going to be phrased, organized in this way to lead you down the correct path. It's important to write down your knowns and unknowns and figure out the equations that solves for what you need. Here's an example, another question from the book. I'm not going to go through it. If this particular 3.4 is confusing you and you'd like to dive into it more, work through 3.5 on your own. Trajectories differ greatly, right? The harder you shoot something off, the farther it'll go. And I'm sure most people are aware 45 degrees is the optimal angle for getting as far as you can, right? This can be shown mathematically, and it's also kind of just how it works, right? A classic equation for this is orbit. Essentially, I think there's a very famous, I want to say Leonardo da Vinci or something like that, or Galileo maybe, did a famous thought experiment where if you shoot a cannon off of the Earth, a cannonball out of a cannon off of the Earth, could you shoot it fast enough that it would never touch the Earth again? And the answer to that is yes, and that's what we call satellites, right? And all this stuff, the math of those equations, the math of satellites, if you take away extraneous stuff like air resistance, is broken down in these triangles that we're talking about here. It's pretty fun stuff. Here we have examples. Another common example is you're going to see of extra motion, right? If you're rowing forward, but the river is going to the right, you are actually traveling to the right as you're traveling forward. All these questions are, when you do them, is variations on exactly what we just did with the firework. Just you need to map this X and Y. Instead of Y being horizontally up, Y is now across the river. Instead of X being horizontally over for the firework explosion, X is the direction of the current or the direction of the wind, right? This example here has a negative component to it. Again, read the book to understand more, but very, very doable, right? More and more triangles. Again, I'm not going over these particular examples because it's rehashing the topic I've already covered. If you'd like me to go into these a bit more with you as individuals, you can get a hold of me. I can try to set aside some time to talk with you one-to-one, or you can ask the questions in the comments, ask your tutors, shoot me an email, whatever you need to do. Cool. That is chapter 3. I hope this lecture was informative. And again, takeaways. 1, everything should be written down. If you're working on it, you need to write it down. If you're trying to do this stuff in your head, it's just all on the calculator and you're getting lost, it's not making sense, take it slowly, write stuff down. Write down your knowns, draw a picture if you have to, write the equations before you actually do them, all that jazz. And 2, this is all just triangles. Chapter 3 is all just triangles. So with that, take care.